going to look at halohydrocarbons, and I'm having some notes here, some theory. We shall call it the introduction, and we shall begin with that part there where we have halohydrocarbons are halogen derivatives. They are halogen derivatives. Halogens, we know them. Halogens are the group 7 elements where we have fluorine, chlorine, bromine, iodine. So they are halogen derivatives of organic compounds. They can be alkyl halides or aryl halides. So this aryl will indicate the presence of benzene. It's going to indicate the presence of a benzene ring directly bonded to the halogen there. So we have our general formula for the halohydrocarbons, which is this, and we know very well R stands for any alkyl group. So that R stands for any alkyl group, and X is the halogen there. Then we have the expanded form of it is this. You find out that this one is it's like an alkane, but it has lost one hydrogen, of which that one is an alkyl group. So this is the same as that. And our X is fluorine, chlorine, bromine, or iodine. Then when we move on to the classes, we have to know these classes. We shall meet them in our synthesis and the reactions there. So under the classes of halogen alkanes, we have primary alkyl halides. So I'm going to be abbreviating this as primary alkyl halides. So I will do this, standing for primary. And how do we know that this one is a primary alkyl halide? It has one alkyl group. So it's only one alkyl group attached to the carbon atom having the halogen. Then for secondary alkyl halides, we shall be abbreviating them as that. So secondary alkyl halide, and this one is going to be primary alkyl halide. So for secondary, it has two alkyl halides attached to the carbon atom having the halogen. Then when we move on to the tertiary, we shall have it as tertiary alkyl halides, and these tertiary alkyl halides are having three. They are three alkyl groups directly attached to the carbon atom having the halogen. So that is it for the classes. Then we can also categorize them under saturated and unsaturated. So these ones are unsaturated alkyl halides, and we know them that these ones have a double bond, a double or triple bond. So existence of a double or triple bond within the chain mix any alkyl halide and saturated. So for those ones that are saturated, we shall have an example like CH3, CH2, bromine. That one, it has no double bond or triple bond between the two carbon atoms. So our bromoethane is a saturated alkyl halide there. So we have the examples. Are you seeing this and that? Those bonds there are indicating unsaturation. Then when we move on to another classification, we have polyhalides. So we shall come across these polyhalides. These ones that are having more than one halogen atom. Sometimes we call them dihalides, and they are grouped under the vicinal, sometimes called the Vic dihalide or gem dihalide. So that is it, Vic or gem dihalide, and this is it. Our 1,2-dibromoethane has two bromine atoms that are bonded to the two adjacent carbon atoms. So these ones are 2. That's why we have one carbon atom attached to one bromine atom attached to the first carbon atom, then the second attached to the second carbon atom. So we shall give it 1,2-dibrom. Then ethane is the parent chain, and we also have 1,2-dibromopropane. 1,2-dibromopropane, the parent chain has 3 carbon atoms. But now we start numbering them from this side, 1, 2, and 3, such that when we mention this 1, 2, we give it the lowest number possible. If you try to sum them up, 1 and 3, 1 and 2 gives us 3. So that is it. Don't give it 2,3-dibromopropane. That's wrong. 2, 3. When you add it 2 and 3, you get 5. But when you add 1 and 2, you get 3. So the lowest is the correct one. So these ones are examples of vicinal dihalides. Now, gem dihalides are having 2 halogens attached to the same carbon atom. And we have an example, 2, 2, meaning they're in the same position. You start counting from here, 1, 2, 3. So 2,2-dichloropropane. Then we are having 1, 1 attached to carbon atom 1. So you don't label it from this side 1, 2. And so 2,2-dichloroethane. That's wrong. We take the lowest value. Then I'm having aryl halides. Aryl halides are those with a benzene ring directly attached to the halogen. So the halogen directly attached to an aromatic ring. Aromatic rings are these benzene rings here. So aromatic rings are the benzene rings Now, as you've been following our interactions, I'm only going to focus mainly on our point of focus is going to always be lab preparations, then we look at reactions, and the uses. We shall also look at tests, but you find out that these tests are under reactions, just that we follow the observation and see what we come out with. So if the observation is physical, if there is some physical color change, we can take that as a test for the presence of the halogen. Then we shall look at the uses and we close the topic. So you find out that this topic is a bit big, but I'm going to be very fast. So our preparations, we shall begin with lab. We shall begin with the lab preparations, and in our lab preparations, I'm going to have the first one is going to be from alkanes. So from alkanes. So from when we prepare them from alkanes, we have two alternatives, but this one we have two alternatives, but one is recommended of the two. There is that reaction that we studied about in alkanes of reacting chlorine in presence of UV light, and we said that reaction is not suitable because it gives very many products, a mixture. But to be more specific, try to use this alternative. It's going to be, see our example. So I'm going to always use simple examples. You have to expand. You have to go and read those books and find very many examples used. My task is to open up a topic, gives you the understanding, and the other part is your revision. So I'm having sulfur dichloride dioxide in the presence of dibenzoyl peroxide, and at a temperature of 40. It's a range of 40 to 80, but now for me, I don't like ranges, so shall take 40. If you give a range, students tend to confuse these things. So that is it. We are forming by the way, this one is this R is very problematic. It may end up bringing problems. So we are having CH3, CH2, chlorine there. So this one is you can either begin with the alkyl group, which is ethyl chloride, ethyl from the word alkyl, from alkyl to ethyl, then chloride, so ethyl chloride, or you begin with the halogen, so you can either say chloroethane, so you're not limited. That is it. Then I'm moving on to reaction 2. So I'm going to reaction 2, which is from alkenes. From alkenes. So when you're moving from alkenes, we shall take an example of CH3, CH, double bond there, CH2, and when I put there my chlorine and my solvent, carbon tetrachloride, I end up with a vicinodihalide, CH3. You realize that we covered this reaction in alkenes. So the reaction in alkenes is acting as a preparation, a laboratory preparation of a dihalide here. So I will not explain much there. We already know the concept. Then you can use that very reaction for bromine, and we have another reaction here. So I'll call this one A. So I'll call it A, falling under alkene reactions. Then part B of the same reactions is going to be, if I decide to say maybe my CH3, CH, double bond, CH2, then I put in hydrogen chloride, and it's in gaseous state, and this hydrogen chloride is dry. I end up with CH3, C, I end up with C, H here, the halogen here, and the CH3. So we are using Markovnikov's rule, if you remember that rule. Markovnikov's rule says that the one with the highest hydrogen atoms will take that hydrogen there. So this one was 2, it gets the 3. Then the one that has the least number takes the halogen, takes the remaining halogen, chlorine there. Have you seen that? So this is Markovnikov's rule. Then we have to talk about the anti-Markovnikov. So I'm going to indicate it here. Markovnikov's rule. So that is Markovnikov's rule. Then anti-Markovnikov. So under anti-Markovnikov's rule, we are going to use anorganic peroxide. For example, we shall use that very example there, CH3, CH double bond, CH2, hydrogen. I will use hydrogen bromide, and anorganic peroxide. So when I put in anorganic peroxide Ig or Ia, we can use R or R. These things are covered in alkenes, reactions of alkenes. So what do we get? With the anti-Markovnikov, it's going to try to oppose that principle up there. So the one with the least number of hydrogen atoms is the one that gets the hydrogen. The one with the greatest number of hydrogen atoms instead is going to harvest the halogen there. I think the halogen is here, and this for Markovnikov, the halogen is there. So we move on to the next, which is our reaction theory. So our reaction theory is going to be from alkynes. And how do we prepare this from alkynes? An example is going to be HCCH, and when I put in excess excess chlorine molecules and silicon 4 oxide and our iron, silicon 4 oxide is acting as a catalyst. What it does, it's going to add 2 chlorine molecules on the first carbon atom, and it will add the other 2 on the next carbon atom there. So it can also work for bromine. Then when we use a hydrogen chloride, what do we get? So this one I will call it my part A. I will call it A of that section. Then part B of that section is going to be, if I'm having that very example, HC triple bond HC, and I add in excess. I add in excess hydrogen chloride, and I put there copper 1 chloride. What do I end with? I end up with CH3, C, chlorine here, and chlorine there. And don't forget our hydrogen. So we have that. Some books are going to be using mercury chloride as the catalyst, but for now we shall use this copper 1 chloride as our catalyst. So that is it. We move on to the fourth, which is from alcohols. Is from alcohols. I'm having an example of a primary alcohol here, CH3, CH2, CH2, OH, and when I add in PCl5, I'm going to end up with CH3, CH2, CH2, chlorine plus POCl3 plus HCl. And these ones are going to be dense. The observation here is dense white fumes. So we shall observe dense white fumes given off as hydrogen chloride fumes. This one was a primary alcohol. What if we have a secondary alcohol here? With the secondary alcohol, I'm going to have CH3, CH, OH there, then CH3, then I add in PCl5. I end up with CH3, CH, chlorine, CH3 plus PO Cl3 plus HCl, and these are the dense white fumes. So when they ask for what was observed, you'll always know that it's HCl that is observed there. So I'm going to call this one my part A. Then part B, I would say this one is a test for alcohols. So under this, we shall find out that when we react alcohols with when I react an alcohol with a dry hydrochloric acid or dry hydrogen chloride in presence of zinc chloride as a catalyst, I end up with an alkyl chloride. So an example, if I'm having my primary alcohol as CH3CH2OH, that is a primary alcohol, and I add in dry HCl and anhydrous zinc chloride catalyst. This one is our catalyst. Then I add in some reflux. I heat. Reflux means heating. I'm going to end up with CH3CH2 and chlorine there. Then when I move on to this one was primary alcohol. Then what if I'm having secondary alcohol there? For example, CH3, CH2, CH3, and I add there my hydroxyl group. So, and I bring in these conditions there. What am I going to end up with? I'm going to end up with CH3, CH, and chlorine, then CH3, like that. So for what we observe in tertiary alcohols is that the reaction is it occurs readily in presence of water and concentrated hydrochloric acid. So with tertiary alcohols, it's going to be maybe CH3, 3 there, OH, Then I add in conc HCl. It's going to give me direct CH3. I add in a 3 there. C chlorine. So that is what we observe there. So we shall dive deeper into the observations when we reach alcohols and their tests, where we shall have maybe a cloudy solution formed within 5 minutes, 10 minutes immediately. I'm going to go deeper in those when we reach a test for alcohols. So this one was maybe. Then I'm going to call this my C. So it's like this, the reactions I'm going to try to write here are specific for if at all you want to add maybe a bromide atom or bromine atom to an alcohol, and specifically tertiary alcohols. So let us try out that one and we see. So if I'm adding oil in the formation of any alkyl bromide, we can use this. It's always from demystifying, it's stated that alkyl bromides can be formed by treating tertiary alcohols with a mixture of red phosphorus and bromine. So we treat tertiary alcohols with a mixture of red phosphorus and bromine. What do they mean? When you mix phosphorus and bromine, it's going to be our phosphorus plus the bromine, giving us, when you heat, we end up with phosphorus bromide 3 there. When you try to balance, it's going to be balance the bromine first with the 2 and the 3, such that you put the 2. Then bring your tertiary alcohol, CH3, 3, carbon bonded to OH. So it's going to be phosphorus 3 bromide there, reacting and giving us a tertiary alkyl bromide. So C and bromine there. So we have that. And this is a very reaction that is used in when you don't want maybe to use bromine and you're using iodine. Same balancing. You use the same balancing, giving us 2p iodine 3 there. So it's the same reaction, though whether you bring a primary alcohol, secondary or tertiary, it's going to give you the same thing. So put there your potassium iodide or potassium phosphorus 3 iodide there. So when you use your phosphorus 3 iodide, It's going to give you CH3, CH3, CH2, and the iodine there. So you can call this iodo. You can call this iodoethane. Or ethyl iodide, but this one is better. So we move on to the next one, which is preparation from aldehydes. Is it preparation 5? Yeah, this one was 4. Move to preparation 5, which is preparation from aldehydes and ketones. From aldehydes and ketones. So generally preparation from carbonyl compounds. How do you prepare alkyl or halogen alkanes from carbonyl compounds? An example is CH3 carbon, double bond there, O, and the hydrogen is there. When we add there PCl5, what do we get? We end up with CH3, C, our chlorine up and down, and hydrogen. This is the major product we get. So I have used an example of an aldehyde, which is ethanol. So this one is our ethanol there. Then the other example I'm having is for a ketone, which is propanone, CH3, O, and CH3. So when I add in PCl5, it's going to give me CH3. So when you look at such a reaction, just understand that it's giving us a gem dihalide. You see, this one's a gem. They are both gemino dihalides. So we move on to going to move on to the 6th. And in our 6th there, we shall look at I will call it halogenation of benzene. So if I'm having my benzene, there, then I add in bromine and iron 3 bromide there. So I end up with that temperature 80 degrees, I'm going to end up with an aryl halogeno alkane, which is this. We shall call it bromobenzene plus hydrogen bromide. This one has a mechanism. So it's the same thing with, if I use a react to my benzene ring, if I use my benzene and I add the chlorine and aluminium ferric chloride, these ones are Lewis acids, and this is one of the importances, that aluminium chloride and the iron ferric chloride. End up with chlorobenzene plus hydrogen chloride. So if I want to add iodine, what do I do? If you're interested in adding the iodine, conditions are going to change for iodine. Sour benzene. So when you bring your iodine, put the concentrated nitric acid and you reflux. So add the conc nitric acid and the reflux. It's going to give you benzene and iodine. So we move on to another reaction, and this one is somehow a chain reaction. It's a chain reaction from, if you want to prepare maybe chlorobenzene, iodobenzene, and you want maybe to use this path, it's also possible. So you get your aminobenzene, get the aminobenzene, then add the sodium nitrite, add the sodium nitrite and dilute HCl. So dilute HCl at 0 degrees Celsius. If you go beyond 0 degrees Celsius, you may end up with phenol. So what do we get here? we end up with benzene diazonium chloride. So we end up with a nitrogen there with a plus and triple bond, nitrogen, and the chloride there. Now, it's this benzene diazonium chloride that we are going to use. It's the benzene diazonium chloride that we're going to use to prepare chlorobenzene, bromobenzene, iodobenzene. So it's going to be, this is our benzene, benzene diazonium chloride. So that is it. So let us now prepare our so how did we call this? Those compounds with the halogen, we called them compound with an aromatic ring, we called them aryl halides. So we are preparing aryl halides in this way. So if I'm having my benzene, let me try to do something bigger. So start by preparing chlorobenzene. So my chlorobenzene is there. These are going to be the conditions and the reagents needed: copper bromide or copper 1 bromide and concentrated hydrobromic acid. So it's going to be copper 1 bromide stroke concentrated HBr, and we shall add there, we shall put in some warming and end up with that. So it's a sum reagent and the conditions are the same needed for preparation of bromobenzene. So now bromobenzene, add there. Here. So this one is a mistake. This one has to be bromine here. Why? Because you're using bromine and hydrogen bromide. So it's bromine, bromobenzene. So when I want to prepare chlorobenzene, I just change the reagents. Conditions don't change. What do I put in? I'm going to put in copper 1 chloride stroke concentrated hydrochloric acid, and I warm. End up with that. Then if I want to prepare iodobenzene, the conditions are going to change and the reagent changes also. So you should just understand that this is going to change in this way. It's going to be copper 1 iodide in aqueous state, then warm. When you warm, it gives you that iodobenzene there. So that is it. This one is an alternative. I'm going to call this alternative A, and I will call this alternative B. So we move on now to chemical properties. I think this one is done. So the journal has been quite long, but let us rush to the chemical properties and see. So you may find out that some chemical properties or chemical reactions are preparations of either alcohols, preparation of alkenes, alkynes. So these things are just playing with ideas. Combine ideas, move on. Combine ideas, move on. So the first reaction is going to be a reaction of, let us first write our heading here. Reactions. So under that, we shall have the first one, which is a reaction between CH3, CH2, so that, and when I add in my sodium hydroxide in aqueous state and heat, this one gives me straight CH3, CH2, OH, and sodium bromide there. I think that it has a mechanism, and in our mechanism I'm going to split it like this our sodium hydroxide is going to ionize fully, giving us sodium ions and hydroxyl ions, like that. So this one's aqueous, aqueous, aqueous there. Now we formed our electron-rich species, so it's going to be our nucleophile. When I mention a term that you don't know, go and read about it in that book, Demystifying Organic. So this nucleophile is the one that is going to initiate the attack. So you find out that this CH3 try to CH2, or I should spread these hydrogens to give space. So I'm having bromine there. Remember that our bromine is electronegative, highly electronegative. So it's going to have a partial negative charge and leaving carbon with a partial positive charge. Now, as my nucleophile comes to attack my electron-rich species, as it attacks that carbon, bromine is going to break off. How are you seeing that? So as it breaks off, we shall end up with loss of our bromide ions, and we end up with CH3, CH2, and OH there. So this sodium and the bromine are going to react. So the lost bromide ions and the sodium ions will end up reacting, forming sodium bromide. So this is it, and this is that sodium bromide explains its presence there in our reactions. So that one was our first reaction. Then I'm going to the second reaction. So I will have to comment about this. This reaction at first is a substitution reaction. So this one is a substitution reaction, because the OH ions, these ones, are substituting the bromide ions there. I think the end result is bromine is no longer in its position. It was substituted. Now, under substitution reactions, we have two forms of substitution reactions. We have substitution unimolecular and bimolecular substitution. So in demystifying, you will find that they are going to indicate it as SN1 and SN2. So we shall try to explain something here. So this one stands for substitution, and that N stands for nucleophilic the same thing with that S there. That one is substitution, and this is nucleophilic. So what we're remaining with is this 1 and the 2. So that one stands for unimolecularity. So substitution, nucleophilic, unimolecular. Unimolecular. And that 2 stands for dimolecular. So this knowledge is going to help us in identifying that primary alkyl halides undergo substitution dimolecular reactions. So this one is for primary alkyl halides. Why? A substitution dimolecular reaction is that reaction having 2 species taking place in the rate determining step. So we shall cover this in physical chemistry. So when you try to look at this reaction, you find out that we are having the OH and the bromine existing in the rate determining step. We are having addition of the OH, and at the same time we are having removal. So that's why we call it dimolecular substitution, nucleophilic. This now what we know about when you move on to, let me call this one my A, then when I move on to secondary alkyl halides, it's going to be a bit different. How? Let me take an example. The secondary alkyl halide such as CH3, CH, bromine there, then CH3. When I add in sodium hydroxide, and the sodium is in aqueous state, and I heat, what happens? We end up with CH3, CH, OH, yeah, OH, CH3 plus sodium bromide there. So our mechanism is going to be, this is why this one is called a substitution unimolecular. This is the reason. In this mechanism, we have CH3, CH3, and OH there, and it's Br. So the Br is going to initiate its own process of leaving. This is a positive carbon atom there, partial positive. So in substitution unimolecular, the bromide ion is going to first leave. It's going to first initiate the reaction, and it leaves. So I'm going to indicate that bromine is there, then CH3, bromine is lost. I'm having hydrogen and this CH3. So this carbon atom is now positive. It's lacking the complete number of hydrogen atoms it should be having. So remember that our sodium hydroxide has dissociated or ionized to give us sodium ions and the hydroxyl ions. So these hydroxyl ions in solution are going to attack immediately and they will form CH3, C, OH, H, CH3. I think that. So we are having two rate determining steps and we are having one species in each. We are having one species in each. There is this step, we are having one species, then in this step we are having, it's only one there. It's no longer a direct attack of OH and the exit of the bromide atom, or the bromine atom there. So that is it. And usually this one's a slow step and this one's fast. We shall go into those details. With time, I want us to first focus at reactions. So for now, just understand that secondary alkyl halides are having such a kind of reaction there. So secondary alkyl halides are having such a reaction. So someone may want to understand, what if I'm having maybe a tertiary alkyl halide? So tertiary alkyl halides are giving us alkenes. So those ones are giving us alkenes, and it's stated that alkyl halides cannot react with sodium hydroxide under some conditions to form phenols. So let me try to. We are having tertiary alkyl halides form alkenes instead of alcohols. So here we were trying to see formation of alcohols. By the way, this one is more of formation of alcohols. So these ones we are forming alcohols, primary alcohol, secondary alcohol. If you want to form a tertiary alcohol, you end up with an alkene. So I'm moving on to reactions with water. Reactions with water. So I want you to understand that tertiary, let me write it here. Tertiary alkyl halides form alkenes under same conditions. Which same conditions? Sodium hydroxide and the sodium hydroxide and heat. So they are giving us alkanes under those conditions. They are not giving us alcohols as we've intended to form alcohols. So what do we do? If you want an alcohol and a tertiary alcohol, you instead use water and boil. So I'm going to say for tertiary alcohols, we use water and you boil it. How? Maybe I'm having such a tertiary alcohol having an aromatic ring. So I'm having a carbon here, CH3, and CH3, then bromine there. It's going to be water, and you boil. So when you boil, you end up with the tertiary alcohol CH3, OH plus hydrogen bromide there. So our mechanism is going to be this is it. Your benzene ring, CH3, bromine, negative, partial positive. So first bromine breaks off and we end up with loss of the bromide ions, and we remain with our aromatic ring and CH3 plus. Now at this very step I'm having water there, but this water has lone pairs of electrons. So using those lone pairs of electrons, our water molecule is going to attack that carbon atom. Our lone pairs are going to attack that carbon atom, and we shall end up forming CH3, or so now oxygen is having excess bonds. It gains a positive charge. In order to neutralize this charge, we broke off that hydrogen there, and we shall end up with a loss of hydrogen atoms, and our benzene ring. So our benzene ring, carbon, CH3, CH3, and OH there. So that is it. Lastly, the last bromine has to react with that hydrogen. So I'm having my hydrogen ends plus Br, and I'm going to get hydrogen bromide as my end product. So this one was reaction. I'm moving on to reaction C. Moving on to reaction C. And for reaction C, I'm having amine formation. Amine formation. And under amine formation, I'm having CH3, CH2, and chlorine there. So this is excess. We are going to use excess alcoholic, excess alcoholic ammonia, and heat in a sealed tube. So you seeing that heating in a sealed tube, some books are going to only give you maybe concentrated ammonia. So some books say just use concentrated ammonia. It all gives you CH3, CH2, and NH2 plus hydrogen chloride. So we have our substitution reaction, and this one is the substitution dimolecular reaction. Why? Because in our mechanism, we shall have CH3, CH2, and chlorine. Chlorine is going to break off, and at the same time our ammonia attacks. So are you seeing that as ammonia attacks, this one breaks off? We are having an attack and a break off at the same time and in the same stage of the reaction. So I'm going to lose the chloride ions and end up with CH3, CH2, and our nitrogen having 2 hydrogens and the third hydrogen, so there are 3. That's why I intend to write those 3 there, but I'm preparing this one to leave, so it's going to be plus. Now, as it is a plus, I have to remove these electrons and neutralize that charge and end up with a loss of hydrogen, and CH3, CH2, CH2, NH2, like that. Then the hydrogen and the chlorine have to react there. So our hydrogen and the chloride have to react to form hydrogen, chloride, that one. Now, that's why you will always find hydrogen chloride there. It came as a result of that reaction. So that is our reaction there. We formed an amine. You may call it aminoethane or ethyl amine. Aminoethane. So we move on to, I want to be fast. If it's a secondary alkyl halide, so this one was primary. If it's secondary alkyl halide, this one was primary alkyl halide. So for secondary alkyl halides, if I'm having CH3, CH, maybe bromo, CH3, and I add the excess alcoholic ammonia or concentrated ammonia, and I heat in a sealed tube. I'm going to always end up with CH3, CH3. I complete this bond with NH2 and hydrogen bromide. So the mechanism is substitution, nucleophilic substitution. But it's unimolecular. It's unimolecular. Why? Because I want you to go on grasping this, that always in our mechanisms for secondary and tertiary alkyl halides, that alkyl halide, that halogen is going to always initiate the breaking of. Why? Because it's electronegative, it's pulling itself away, and it has that component of negative inductive effect. Are you seeing that? So as it goes off, it's going to always give us, and usually books write this as a partial, as a reversible reaction, giving us H3 C plus H, CH3. Then I'm having my ammonia My ammonia in solution has lone pairs of electrons. This one is similar to oxygen. So what it does, goes and combines with that, forming CH3, CH, ammonia, CH2, and hydrogen there. Now, this one has a positive charge there. Why? Because it's having excess bonds. Now, in order to neutralize that charge, I break off that hydrogen. It remains with CH3, CH3, and our amine. So we end up with that amine there. So we shall call it 2-aminopropane. 2-aminopropane. Why? The amine is at carbon atom 2. So 1, 2, 3. So it's 2-aminopropane. Then we move on to the other one quick. So I want us to realize something here. It's not always that ammonia is the only reactant. So I may bring a reaction where I'm having aminomethane, aminoethane, such reactions. So let me bring, maybe it's not always ammonia. It's not always ammonia, but we can also have aminomethane doing the job. Or let me just write R NH2. Any amine can do the work, and this is what I mean. If you bring secondary amines, we can, maybe if you intend to form secondary amines can be also, or can be formed by reacting a primary alkyl halide and a primary amine. So an example can be CH3, CH2, chlorine there. When I add in CH3, NH2 as my primary amine, so this one is in excess, I'm going to form CH3, CH2, our amine, hydrogen, CH3 plus HCl. So in our mechanism, this is what happens. We know that this one is the substitution dimolecular reaction. Nucleophilic substitution dimolecular. It's going to be CH3, CH2, your chlorine. Then This one's partially negative, partially positive. So I'm also having my amine CH3. Today, it's not ammonia doing the work. It's going to be our methylamine, our aminomethane. So as it attacks, this one gives off so I'm having loss of the chloride ion, and I end up with CH3, CH2, and bonded to nitrogen. And I'm preparing this nitrogen, since it has 2 hydrogen atoms, I'm preparing 1 hydrogen to move off. Then I include that CH3 here. You see that, so nitrogen has how many bonds? It has 1, 2, 3, 4, and those are too many, they are excess. So what do? We get these electrons here and add it to nitrogen. As we add them to nitrogen, we neutralize that charge, but on the expense of the loss of hydrogen there. So it's giving us CH3, CH2, nitrogen, single H, like that. Then the hydrogen that is given off reacts with the chloride ions, giving us hydrogen chloride, like that. So this is the mechanism. And we formed secondary amine. We formed the secondary amine. Then we have another one, and it states that tertiary amines can be formed by reacting a primary alkyl halide with a secondary amine. So formation of tertiary amines. So this one was, I'm going to summarize it as formation of secondary amines. Then this, by the way, this one is also secondary amine, but for it it's unique. Secondary amine, and from our reaction here we formed a primary amine. So this one is primary amine. That X is going to be standing in for something else. Let us abbreviate it as RN, stand for the amine. So I'm going from tertiary amines from primary amines and from secondary amines and the primary alkyl halide. So formation of tertiary amines. Now under tertiary amines we are having a reaction of this kind: CH3, CH2, NH, CH, 3 plus CH3, CH2, and iodine. This is excess, forming so let me first wait to add there the products. I want us to generate the products from the mechanism. So our mechanism is going to be so it's going to be CH3, CH2, iodine, partially negative, partially positive. So iodine first to break off because of the presence of this amine CH3CH2 NHCH3, like that. So I'm going to attack using those lone pairs of electrons on nitrogen. As we attack, we lose we lose the iodine ion. Now it's going to be CH3, CH2, then nitrogen. With that hydrogen, I'm preparing to lose the hydrogen. Now I'm having this CH3 bonded to nitrogen, and I'm also having this CH2, CH3 bonded to nitrogen. That's how I've decided to illustrate them, because these two are all linked up to nitrogen. So the orientation doesn't matter. What matters is that you should always observe the bonds. Are they excess? Therefore, for is excess, we have to take off this. We have to break off. Oh, it's disturbing. Let me try to expand it. We have to break off that hydrogen. As this hydrogen breaks off, we form something very stable: CH3, CH2, nitrogen is there, CH3, and CH2, CH3, like that. So this one is now a tertiary amine. So you observe that tertiary amines are having 3 alkyl groups surrounding the nitrogen, and they have no hydrogen directly attached to the nitrogen. 3 alkyl groups. tertiary amides. And when you look at the primary amine, it has only two alkyl groups, this one and this one. So instead of the third alkyl group, we have hydrogen there. So only two alkyl groups. Then for primary amines, we are only having one alkyl group attached to the amine, and what is left is two hydrogens there. So that is it. Then I want us to talk about for the mechanism it's done. I want to go to something else. Ether formation. Ether formation. As my part D. So these alkyls are very many banang. Ether formation. I'll try to break down the topic, but the thing is still big. So we shall move faster. We shall move. So I'm having my reaction number 1 under ether formation as CH3, CH2, bromine. So let me try to make this a little bit longer, like that. So I'm having sodium there. When I add in CH3 and CH2, OH, then I add their heat. What do I form? This reaction is very specific for such alkyl halides, short chain alkyl halides and primary alkyl halides. They are always going to form ether, and the reagent is potassium hydroxide or sodium in presence of an alcohol. So for this case I'm using sodium. We can also use sodium hydroxide and end up with an ether. CH3, CH2, or CH2, CH3 plus sodium bromide there. So did we complete this reaction up here? We didn't. So this is what we put down there. So it's going to be CH3, CH2, and CH3, CH2, CH3. So when we try to work out the mechanism, it's going to be, by the way, what's our title? We are dealing with halogen or halohydrocarbons. It's Halohydrocarbons. So we're still talking about our mechanism. And in our mechanism, we have this sodium. You know, at some point, alcohols behave as though they are acids, because this reaction is a behavior of acids. Reaction with alcohols react with these metals like sodium, potassium to form metal. Their metal like CH3, CH2, or sodium. So we call this one sodium ethoxide. I think that sodium ethoxide, and we form hydrogen. We liberate hydrogen, but due to the fact that we have to balance it as one hydrogen lost, it's going to be that half there. I think that. So now this sodium ethoxide has to dissociate. It's going to dissociate to give us ethoxide ions plus sodium ions. Now it's the ethoxide ion that is going to attack this halogen. It's going to attack bromoethane in this way, CH3, CH2, bromine, partial negative, partial positive, and this is what is going to happen. CH3, CH2O minus, so that attacks there, and our bromine is going to break off, and we lose that bromide ion, ending up with CH3, CH2O, CH2, CH3. So this is this. This part is this part, and this is this. Oxygen is now linking the two, and the bromine is lost there. So now the lost bromine and the sodium are going to react. So it's sodium ions and the bromide ions reacting to form sodium bromide, like that. So someone may want to use maybe a hydroxide. For example, you may think of maybe using a hydroxide instead of that metal. For example, maybe CH3, or let me use a benzene ring. Let me use benzene attached to maybe CH2, CH2 and bromine there. Bromine. Then I add in potassium hydroxide and ethanol. Add in ethanol. So when I heat, so it's going to give us CH2 or CH2. It depends on the number of carbon atoms we've brought to. So I'm going to add there 2 and 3 there plus. Now the potassium will react with the bromine to give us potassium bromide. The only unique part in the mechanism is which it's not as unique as such. It's just potassium hydroxide is going to react. The way sodium reacted with alcohol to form a salt and water. So I'm going to form CH3, CH2, potassium ethoxide and water. Now the rest are the same. The potassium ethoxide dissociates. The potassium ethoxide is going to dissociate. After dissociating, it will give us potassium ions and ethoxide ions. The ethoxide ions are going to attack the halogen, breaking off the bromine. If you have chlorine, it's going to be chlorine breaking off, and we form our ether. So I'm not going to complete this. I'm going to march forward. So, and I will give you some examples that they can be. Such an example can be presented to you to complete, and you may say, we didn't study that. So they're just playing around with ideas. So they may give you this. They may give you an ethoxide, sodium ethoxide, sodium phenoxide, because this is pheno. When it has OH, it is pheno. So when I remove this H and I make it sodium, it is sodium phenoxide there. So it's that's how we name it, sodium phenoxide. And heat, what do you say? You have to write the products as your benzene ring and oxygen there. Then I'm going to add this, since I'm aiming at forming an ether. So that is it. Then sodium ends up reacting with iodine, forming sodium iodide. So what you were struggling with with these mechanisms, we were struggling to form the ethoxide ion. But today, that such an ion is already prepared, sodium phenoxide. So what else do we need to do? We need to dissociate it. So dissociation, then reaction. Are you seeing that? So we need that there. So you will complete the mechanism. I'm moving on to something else, and that is ester formation as my reaction E. I'm going to call it ester formation. So under my ester formation, I'm having a primary alkyl halide. Remember, we are still under reactions of alkyl halides, whether primary, secondary, vicinal, GM, anything. We are trying to explore their reactions. So you can always have this, maybe I'm trying to form an ester, CH3, C minus silver. So this is silver ethanoate and ethan, and you want silver ethanoate. What do you end up with? You end up with CH3, CH, nope, or so where there was silver, I'm going to add these two to make it CH2, CH3 plus silver bromide. So I think that it's a substitution reaction, and it's that kind of reaction where silver is being displaced. So where there is silver, we shall replace with this ethyl group there. So mechanism is following the same trend. So it's going to be first our silver ethanoate is going to dissociate and give us ethanoate ions, and silver ions. Now the ethanoate ions are going to attack this. I'm having my primary alkyl halide with bromine, and this one's partially negative, this one's partially positive, such that CH3 as this goes there, this one is going to break off. Now as it breaks off, I'm having a loss of bromide ions. I remain with, I'm going to remain with CH3, C, H2, and O, C, C, H3. So don't be confused with these two. They are the same. It's just that this part is the last part here, and it's the first part here. As long as I maintain this OO on this carbon atom without hydrogen, I think I maintained that OO on one carbon atom without any hydrogen. So in actual sense, it's going to be CH3, C with a double bond there, bonded to carbon atom, and the carbon atom bonded to CH2, CH3. That is it. So it shouldn't confuse us. Those two are the same. Then I want to move on to, by the way, what we formed is an ether, an ester. So this one is called, you start naming it from so just look at where it came from. It came from ethanoic acid. This part came from ethanoic acid. So, and this part is called we shall call it the ethyl. So it's ethanoate. So this is ethyl. It's going to be ethyl ethanoate. Ethanoate coming from ethanoic acid, and the ethyl coming from the ethyl group. So we march on to the mechanism is done. I'm moving on to nitrile formation. So this is E. Now I'm going to F, and I'm going to call it nitrile formation. So under our nitrile formations, we have an example: CH3, CH2, and bromine. So when you put in potassium cyanide and aqueous ethanol, and you heat, what it does, it's going to give you CH3, CH2, and CN, like that. So you realize that when we talk of nitriles, When we talk of nitriles, we mean such compounds with the nitrile group, or with cyanide. They are got from potassium cyanide or sodium cyanide. So what happens is that this Cn here comes and replaces bromine. So you will get to know that such a reaction increases the carbon chain number, or the number of carbon atoms on our reactant. So we've increased the carbon atoms. So try to identify those reactions whenever you're reading organic chemistry. Try to identify reactions that increase the carbon chain and reactions that decrease the carbon chain. So this one's among them. We also saw certain reaction under ester formation. So I'm having this, but now after reacting, or after the reaction, I'm having 1, 2, 3, 4 carbon atoms. Yet I had 2. And it's the same thing with ethers. So ethers, for this case, we had 1, 2. We had 1, 2 carbon atoms, and we have 1, 2, 3, 4 carbon atoms. So you're tasked to always identify those reactions that increase or decrease the carbon atom number. So which one, when you look at the mechanism, it's going to be our potassium cyanide dissociating to form potassium ion. So potassium cyanide dissociates to give us potassium ions, and the cyanide ion. Now this one is a substitution reaction, and it's a dimolecular substitution. Why? It has 2 species in the rate determining step, CH3, CH2. I'm having bromine, then I'm having my nucleophile. I said a nucleophile is that species that is rich in electrons, electron rich. So as it attacks, it's going to displace that bromine off. Now, as our bromine goes off, our bromide ion, we end up with CH3, CH2, and the cyanide sits there. Then potassium and bromine have to undergo their independent reaction to form potassium bromide. It's the reason as why it's included here. Potassium bromide. So what do we call this? We shall call it propan, because it has 3 carbon atoms. So propan nitrile. It's called propan nitrile, like that. So that one is the mechanism. I'm moving on to another reaction. So we later in our chemistry we shall understand that maybe let me put it as a sidewalk here. Nitriles are not talked about so much, so we are tasked to always talk about them as we move on. As we cover different organic compounds, when we come across a nitride, we talk about its reaction. So in this case, we have such a reaction of propan nitride reacting with acidified water on heat. What does it give us? It gives us CH3, CH2, C, OOH, like that. So it gives us a carboxylic acid. Gives us a carboxylic acid. And so we move on to G. So when I move on to G, is a reaction with sodium acetylides. So when I react sodium acetylide, you get to know that this reaction, we covered it in chain elongation. We covered this reaction in chain elongation and alkynes, where we used sodium in liquid ammonia and formed the acetylide. By the way, we've not named this. This one's reaction with sodium acetylides, like that. So I'm having this reaction and it's going to give me CH3, C, H2, C, triple bond there, CH, plus sodium bromide. So when you try to look at the mechanism, I hope you people have started seeing the pattern, and if you to guess, you shall first dissociate that acetylide such that we make a nucleophile. There are always nucleophiles or electron-rich species that are doing the work. So it's sodium there. Then it's going to be HC. No. So after getting our acetylide, it's going to attack the halogen. Sodium, it's going to attack bromoethane, and we break off this bromide ion. So it's going to be CH3, CH. Let me put the hydrogen behind C. So it attacks using that. Then as it attacks, this has to break off, and as it breaks off, the bromide ion is gone. I'm remaining with CH3, CH2. Then I begin adding on this acetylide like that. Then the sodium and bromine, sodium ion and the bromide ion are going to break up and give us sodium bromide. So you're seeing that it's the reason as why sodium bromide is there. So don't always skip out this reaction. Usually students only end on that reaction and they forget this, thinking that it's a minor reaction, but usually you may find a paper that has a marking point there, so you may lose that marking point. Then we move on to H. When we move on to H, it's going to be a reaction that we shall talk about more when you're covering benzene, but we shall talk about it. So H is preparation of alkyl aromatic compounds. So preparation, we are still under reactions of halogen alkanes. So preparation of alkyl aromatic compounds. Now, which kind of reactions are these? I'm going to put here a hashtag on it. It's we shall call it alkylation, Fidel Craft's alkylation, but we shall talk more about it when we reach the alkylation. So what do we expect in this? When you have your benzene, whenever you see that word aromatic, just know benzene is the chief there. So if I'm having my benzene and I add in maybe CH3, CH2 and bromine, then aluminium 3 bromide, what do we end up with? We end up with so we end up with that alkyl group, this one. We shall add this on the benzene. It's what you're interested in. So I'm going to add it there. CH2, CH3. So this reaction can be regarded either nucleophilic substitution or either an electrophilic substitution in the benzene ring or nucleophilic substitution by the aromatic compound in the alkyl halide. So we shall look at its mechanism when you're covering benzene. So these ones were reactions, and there were substitution reactions. All these are substitution reactions. Very many of them. Leave alone the preparations. All these ones have been substitution reactions. Substitution reactions, and we've seen that we have substitution nucleophilic unimolecular and substitution nucleophilic dimolecular. Go and make research about those terminologies there. For me, I'm continuing with elimination reactions. So we can also have bimolecular elimination and unimolecular elimination reactions. So examples of this are going to be so I'm going to break to, we are still moving on with the reactions, but we've moved on to phase 2, which is elimination reactions. And under this, I'm having E1 or elimination unimolecular and E2 elimination bimolecular. What is an elimination reaction? An elimination reaction is a reaction which involves removal of an atom or group of atoms from two adjacent carbon atoms to form a multiple bond. So this one is removal. Elimination reactions, we have removal of an atom or group of atoms atoms from two adjacent carbon atoms to form a multiple bond. So to form a multiple bond, that is a simple definition for elimination reactions. I'm moving on straight to the examples that we are having, and I'm going to cover an example. We have okay, let me put this. Our example is going to be CH3 and bromine there, So this one is having potassium hydroxide and ethanol, and you heat. What do we form? So it's going to be from our mechanism. I'm going to generate the answer from the mechanism, and from our mechanism it's always the alcohol to react with the base CH3 CH2OH, giving us CH3 CH2O and potassium, like that, plus water. Now this is going to dissociate so potassium ethoxide will dissociate into CH3 CH2 plus potassium ions, like that. Now we know very well that such reactions having such alkyl halides that are secondary, for example this one, a secondary alkyl halide undergoes unimolecular reactions. How? The bromine first breaks off. That's when we think of bringing in the nucleophile. So this one gives us CH3 C plus our hydrogen down, then I'm having CH2 and hydrogen. I'm preparing this hydrogen to go. So this reaction, people they may think of confusing this with ether formation. Ether formation is different from ether formation is falling under elimination reactions, is under substitution reactions. What I mean, substitution reaction. But if you look at this one is an elimination reaction, and sometimes we call it dehydrohalogenation. So from our definition, removal of an atom or group of atoms from two adjacent carbon atoms to form multiple bonds. So for now, I'm going to remove group of atoms. I'm removing bromine, I'm going to remove hydrogen. That's why I'm preparing this hydrogen for removal, that one. So this is what is going to happen. CH3, this very one that we formed here, the ethoxide, is going to come and fetch the hydrogen, and this hydrogen will give in or will submit its electrons to form that bond there. So CH3 C hydrogen double bond CH. Now we are left with two hydrogens there. Have you seen that? So lastly, this potassium has to react with the bromine. So potassium ions with bromide ions we form potassium bromide there. So that one is our reaction, and I'm going to put it there as the result. It's going to be this. Position it there, and the potassium bromide also position it there. So we shall add there a plus like that. So we move on to another reaction. So we've seen elimination reaction in formation of an alkene. We saw this in formations of alkenes. Then I want a vicinodihalide. Vicinodihalide to also contribute something to our knowledge. So it's going to be an example, CH3, CH3. Okay, let me use this CH2 bromine, CH2 bromine, and when I add the potassium hydroxide and the ether, and you heat, what do we get? We shall find out. Let us first move on to the mechanism. But I'm going to refer you to formations of alkynes. Go and watch my video. I recorded a video. That lesson, we had a lesson under formation of alkynes. So go and watch that video, then you will understand this mechanism. So potassium bromide. So that is it. We move on to, for the interest of time, I'm going to skip these mechanisms. Why? I've covered this work earlier. Earlier on we covered this work. So it's not going to be advantageous for us to repeat concepts. It's not going to be good for us to do that. And when you look at, we've seen vicinodihalides. Then when you want to look at maybe a unimolecular reaction, this one was for secondary alkyl halides, we are seeing unimolecular reactions taking place, and for this case it's elimination unimolecular. It's the same thing with tertiaries. So it's the same thing that is going to happen to tertiary alkyl halides. Are you seeing that? It's the same thing that is going to happen there. So what do I mean? Bromine will first go, or the halogen will first move off. Then we think of which hydrogen are we going to eliminate from which carbon. And here we usually say that the carbon atom that loses bromine will never lose hydrogen. The one adjacent to it is going to lose hydrogen. So that is it. Then I will move on to reactions with metals. So we'll go on to another kind of reactions. So reactions with metals. And under this, I'm more interested in these ones are now, we are no longer in elimination or substitutions, no. So I'm going to call this one my reaction A with CH3, CH2, and iodine there. We covered this under formation of alkanes, dry ether. If you want to revise alkanes, go to my YouTube channel. I'm having that work there. Dry ether. I've summarized it in a way that it's Form 6 friendly. You don't waste much of your time in theory, reading this, reading that. No, go direct to synthesis reactions. Synthesis reactions, like that. So I'm going to end up with CH3, CH2, then CH2, CH3, like that. So what are we seeing? This is doubling, and this is what we call the Watts reaction. We call it Watts reaction. So it's going to double 1, 2, like that. So move on to the next one, reaction B. So reaction with magnesium. So reaction with magnesium. You can call it formation of Grignard reagents. So formation of Grignard reagents. For all those that I've covered this, you know very well that Grignard reagents of this kind are magnesium and a halogen at the end. And whenever we talk about Grignard reagents, we have to go deeper into those reactions of Grignard reagent to have some competency there. So I'm going to move on to the example. If I'm having my alkyl halide as CH3, I'm having CH2, bromine, and I put in magnesium. That includes, dry ether is there. Dry ether. It's going to give us CH3, CH2, magnesium, and the bromine there. So This one's called ethyl magnesium bromide. Ethyl magnesium bromide, like that. That's how we form it. So this Grignard reagent is highly reactive and can be used to prepare alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, and carboxylic acids. So are you seeing all the uses of this? So it's always important to talk about Grignard reagent. So we have to recognize that this Grignard reagent is highly reactive, and it's used in in preparation of 1. Preparation of alkanes. 2. Preparation of alkenes. 3. Preparation of alkynes. 5. Preparation of alcohols. And 6. Carbonyl compounds. Carbonyl compounds. When I talk of carbonyl compounds, just know aldehydes, aldehydes and ketones. Then it's also used in preparation of carboxylic acids. So we march on to preparation 1. I'm going to rush through it quickly. So I'm going to alkanes. So preparation 1, which is preparation of alkanes, and under this we have this reaction CH3 CH2 iodine, and when you add in magnesium and the dry ether, do you know what you form? You form Grignard's reagent CH3 CH2 magnesium and iodine there. So that is ethyl magnesium iodide. Then when you add there water and dilute hydrochloric acid or dilute sulfuric acid, so water and dilute HCl. I will prefer HCl, simple. So it's going to eliminate this, and we add hydrogen there. So we shall add hydrogen on that one. We end up with CH3C. What was H2 is now H3. So we've prepared ethane from Grignard reagents. So what I want you to know, this is what we call Grignard. So Grignard reagent. So there are very many kinds. We have very many types of Grignard reagents because these alkyl groups are very many. You may form a Grignard reagent of 3 carbon atoms, 4, 5. So there are very many. I'm going to preparation of alkenes copy. I will paste it here. Try to enlarge it. Okay. No. Let us first cover that this part. I'm moving to preparation of alcohols. Why? You will find out that if you want to prepare alkenes and alkynes, you may first go through alcohols. So you first prepare alcohols, then you dehydrate the alcohol and get the alkene, then halogenate the alkene to form a dye, a vicinodihaloide. After the vicinodihaloide, you dehydrohalogenate it and get the alkyne. So those ones are very many steps. So I'm going to jump to preparation of alcohols. And in preparation of alcohols, we use carbonyl compounds. So preparation of alcohols from methanol. So I'm going to start from methanol, which is an aldehyde. So HCO. When I add there any Grignard reagent of any kind, it's going to give me, I should always put there dry ether, and it gives me R. It gives me R CH2 or magnesium and the halogen there. So this is the alkyl and this is magnesium and the halogen. After that, I have to add there water and dilute HCl. When I add there dilute HCl, it gives me R CH2 and OH, like that. So using this, we formed a primary alcohol. We formed a primary alcohol. For example, you may want a valid example. I'm having H, C, O, or some people may want to write it as C, double bond, oxygen, hydrogen, hydrogen. That one is methanol, and CH3. So this one is also one of those reactions that increase the carbon chain. Dry ether, we end up with CH3 and C. So what Grignard does, it gets this the alkyl and adds it to that carbon atom. So this is what I mean. So the alkyl is added to the carbon atom. Then after adding it there, remember this carbon atom is having 2 hydrogen atoms there. Don't forget that. And it has oxygen having a double bond, but now it's going to break that double bond and spread it in that way, such that magnesium shares one bond like that. So this is how it does it. Gives our carbon and the alkyl group, and the magnesium ends up taking one bond. So one bond has to go and associate with magnesium to form that association there. So after that, we add in water. Some books will say acidified water, and dilute HCl. So this word dilute is not allowed in our chemistry. That abbreviation, it's always better you complete that statement there. So it's going to give us H3, CH2, oxygen, and hydrogen there. So that one is a primary alcohol formed. So if you want an alkene, you go on to dehydrate. So if you want an alkene, you may go on to add in conc. For conc, it's allowed concentrated sulfuric acid at 180 degrees Celsius to give us C, double bond C, H2, H2. So those are the alkenes. So if you want an alkyne, you halogenate that alkene. Then I'm going to preparation of, we've seen that whatever we've prepared here is a primary alcohol. So this one is a primary alcohol, and I will note that it's only methanol that forms primary alcohols. It's only methanol, this one, C, double bond, O, HH. It's only methanol. others don't do it. So when you want a secondary alcohol, you're going to use another aldehydes. So other aldehydes, I'm going to write it here as other aldehydes from secondary alcohols. Then ketones from tertiary alcohols. So that is the chemistry. So I'm going to give some two examples, then we move on to something else. And my first example is going to be if I'm having ethanol, my ethanol and I add in maybe CH3, CH2, and if I add in Grignard reagent there and the dry ether, we saw what this does is that we shall get the alkyl group, this, and we add it to this carbon atom, then magnesium and its bromine will come and interact with the oxygen. So what we end up with is CH3. So carbon will only remain with one bond with the oxygen, the other one is taken by magnesium bromide there. So we have our hydrogen. I'm going to put this hydrogen down. Orientation doesn't matter. Then the alkyl group is going to be added to that carbon atom to form that. So you've started seeing how things are building. And I add in water and dilute HCl. So I'm going to end up with CH3, COH, hydrogen, CH2, and CH3, like that. Then I'm going to move on straight to preparation of tertiary alcohols as my second example. So use this example to build more and more understanding. So if I'm having maybe my carbonyl compound, which is ketone, we've said that ketones are producing, so ketones form tertiary alcohols. So I'm having my Grignard reagent as this. It's going to be dry ether and it's going to give us R C. We know very well that this R is going to be taken up by that carbon atom, and magnesium will go for the oxygen there. It means that this gives us R and our R prime prime. Then the oxygen atom, then magnesium, and the halogen. Now what is essential, or what is the difference come? The difference between all these reactions is that here we're using dilute HCl, but we no longer use dilute HCl in formation of tertiary alcohols. We use water and ammonium chloride. Ammonium chloride, which is aqueous, and it forms R C R OH R prime prime, like that. So we have three alkyl groups surrounding the carbon atom, holding the function group. So this is it. The only difference comes in here. So I'm moving to the other part, preparation of ketones. So under our preparation of ketones, so this is preparation of ketones. And in this reaction, we have Grignard reagent and Grignard reagent there. Then I'm having added to a nitrile. So as I add it to a nitrile, it's going to be dry ether and 0 degrees Celsius. So what we get is R C. So this is what Grignard does. It's going to give this, that R, or that alkyl group is going to be given to that carbon atom having nitrogen, such that one bond is taken. We remain with R prime and 2 bonds there, and that bond is going to be taken up by magnesium and that halogen it's moving with, such that when I add there water and dilute HCl, I end up with R C. So I'm going to end up with R, then R prime, double bond, nitrogen, and that nitrogen is going to be taken away such that we end up with oxygen there. So for this case, when we add in water, I want you to imagine that during formation of ketones, this oxygen is going to come and sit in this position. For understanding, let us take it that way. That oxygen is going to replace the nitrogen and magnesium and the halide or the halogen, such that we form a ketone. So if I'm to arrange this, it's going to look like this, and that one is a general formula for ketones. So you may go on to expand and look at how this is going to work out. Look at how this is going to be. Add the grignard and move on. So I'm going to jump straight to, maybe they can even tell you to convert. You can be told to convert this cyanobenzene to this CH2 CH3. So for me, I'm moving on to preparation of carboxylic acids. Preparation of carboxylic acids. How do we prepare carboxylic acids? Remember, we are still handling Grignard's reagent. So if I'm having my Grignard reagent as this, then I add in carbon dioxide and dry ether. What do we form? This is what Grignard does. So do you know that our carbon dioxide is of this kind? If you try to look at its structure, this carbon dioxide is of this structure. So what Grignard does, it's going to give this alkyl group to that carbon atom there, such that this carbon atom, which was having two oxygen atoms bonded together, this is what happens. It was once like this, but now Grignard will take off that bond and give it the alkyl group. Then that bond is going to be taken there, and magnesium bromide sits there, such that after having this, some books may write it as RCOO magnesium bromide, like that. It has no problem. Orientation doesn't matter. What matters is the chemistry. So add there water and dilute hydrochloric acid. So what do we form? So when we add the dilute hydrochloric acid, this is going to be taken off and be replaced with hydrogen ions, with hydrogen atoms there. So it's going to be R C O O H, like that. So there we've prepared the carboxylic acid. So we are done with Grignard's reactions. So I'm moving on to reactions. We are still under reactions of alkyl halides, and for now we are looking at dihalides. So reactions of vicino and jamino dihalides. So what happens here? I'm going to start with reaction A, which is hydrolysis. And under this we have CH2 chloro, CH2 chloro. When you add the sodium hydroxide and aqueous, when you heat, it's going to give you a diol, which is CH2 hydroxyl. How do we call this? It's called ethane 1,2 diol. It's called ethane 1,2 diol. If you have propane, it's going to be propane 1,2 diol. So I'm moving on to reaction B, which is reaction with alcoholic potassium hydroxide solution. So And when I talk about reaction with alcoholic potassium hydroxide solution, I mean that reaction that we had under elimination reactions. So I mean that reaction where we had potassium hydroxide and ethanol at the condition was heating, and we ended up with, let me try to summarize it here. It can be either a gem or a vicinal dihalide, like that, and it ends up giving us an alkyne of that kind. So we covered this, we covered that. Then I'm going to reactions with reactions of aryl halides. So under reactions of aryl halides, I'm going to concentrate on reactions of aryl halides. I'm going to skip them. We shall cover this when you're covering benzene. This one we shall cover next. This one we shall cover next when you're looking at benzene. Yeah, that. So I'm going to skip that and go straight to I will go straight to distinguishing alkyl halides and aryl halides. So what I want you people to know is that, so something brief about aryl halides. Aryl halides are those halides with benzene ring. So it can be where X is chlorine or bromine or iodine, like that. So how do we distinguish these ones? When we use hot silver nitrate solution and ethanol, or I'm going to use the lab test to distinguish them. I'm going to use the laboratory test, and under our laboratory test, so let us just say distinguishing alkyl halides and aryl halides. So the reagent is hot sodium hydroxide solution, followed by dilute nitric acid, dilute nitric acid and silver nitrate solution. So that one is the reagent there. It's very long, but that's how you state it. You include the reactants and the conditions. So for alkyl halides, we are going to have an example. If I'm having CH3, CH2 and chlorine, what do we observe? This is what we observe: a white precipitate. White precipitate. Then if I'm having CH3, CH2 and bromine, I'm going to end up with a pale yellow precipitate. Then if I'm having CH3, CH2 and iodine, I end up with a yellow precipitate. Now, that is it. So if you want to identify whether something is having chlorine or bromine or iodine, the alkyl group, If our halogen alkane is a chloroethane, use this reagent. That reagent will give you a white precipitate as feedback. So that's when you will understand that there is chlorine. So I'm moving on to what really happens when we try to maybe distinguish this with aryl halides. If maybe okay, let me first try to explain something here. I think this when we try to look at this hot sodium hydroxide solution, the purpose of that sodium hydroxide solution is to displace the halogen. If I'm having CH3, CH2 and the halogen there, and I add in sodium hydroxide, you remember that, let me put it up. You remember that when you put in sodium hydroxide and heat, that's what we call hot sodium hydroxide solution. What it does, it's going to give us an alcohol. Then, as it gives us an alcohol, sodium is going to take the halogen there, such that it becomes sodium, either sodium chloride or sodium bromide. So, and this sodium chloride is in aqueous solution, so it's going to dissociate sodium plus the halogen. So let me do this. Sodium in aqueous state will dissociate to sodium ions and the halogen or the halide ions. Now, when you add in dilute nitric acid, the dilute nitric acid, so the dilute nitric acid is going to neutralize. So this one is going to, it's like you've added there hydrogen ions. By the way, when you add in an acid, it's like you're adding hydrogen ions to solution. And what are these ones going to do? These hydrogen ions from the dilute nitric acid are going to react with the excess hydroxide ions in solution. So this one is like taking precaution. If you add the excess sodium hydroxide, you have to add there sodium, to add there dilute nitric acid, such that we neutralize these to water. It's better the solution stays acidic than alkaline. Why? Because at the end, I'm going to add there silver nitrate. So if silver nitrate finds there in the hydroxide ion, it's going to react with those hydroxide and gives us a wrong result. Silver hydroxide, which is also a white precipitate. So better we remove them such that when we add there silver nitrate, when you add there silver nitrate, this silver nitrate is going to ion dissociate and give us silver ions, the nitrate ions. So silver ions are going to, remember it's the same solution, so these silver ions are going to locate the halogen or the halide ions and end up reacting. So as they react, we form silver halide, which is also a precipitate. So if this X is our, if this halide is a chloride, then it gives a white precipitate. If it's a bromide, it gives pale yellow. If it's an iodide, it's going to give us it will give us yellow. So this one will give us white. So this one white, this one pale, yellow, and this one yellow, like that. So that one is the chemistry behind that. So I will wind up. Things that I've skipped are things concerning these. I will talk about them when you're talking about benzene. So uses of halogen or halohydrocarbons. Uses of halohydrocarbons. So one of the uses is chlorobenzene is used in manufacture of phenol and DDT. So chlorobenzene is used in manufacture of phenol and DDT. So you shall cover this DDT in biology. It's an insecticide. Then hydrofluorocarbons are used in air conditioners and refrigerators. Then tetrafluoroethane is used to make Teflon, an important polymer. Fluorochloro derivatives of methane and ethane are used as aerosol propellants in dispensers to kill flies, and sometimes they are used as shaving creams. So I'm going to leave this as your research. So this one is research work. Look for this. Look for the uses of these halohydrocarbons. So this is what we've covered for today. This is what we've covered. So I consider this topic as now a gone case. We've seen the lab preparations. The lab preparations were few, but the reactions are very many. The reactions are very many.